এটা তো বেসিক্যালি দুটো স্ক্রিন স্প্লিট করে দেখাচ্ছিস নাকি? না না না, সঞ্জয় সরকার, আমার এটা দেখতে পাচ্ছি। আজকে তো মনে হচ্ছে কেউই জয়েন করবে না। কেন রে? মিটিং এ Hello. So today's class was rescheduled. The last Saturday I couldn't take the class, and I asked them to reschedule it, and they rescheduled it to this Wednesday. So I don't know if they have circulated this because no one has joined. Only one I can see. Okay. Hello. So in today's class I will talk about magnetism, and we'll solve few problems from magnetism. So that okay, shall we wait for 2-3 minutes? Maybe people are joining now. Give me a couple of minutes. So let me share my screen, and then we can start. So so let me share that. This was assignment 11. This I'm going to share. Sorry. Yes. So this is class number. The last class was 10th class, I guess. Yeah, so this is 11th. And this Saturday we'll have the last class, that is the 12th class. Today is 11th October. So today we'll solve few problems from magnetism. So I guess everyone knows about paramagnetism, diamagnetism and ferromagnetism. I'll not go into the details of the theory. I'll start solving few problems. I think in the class the teacher has already taught about the classical and quantum theory of this diamagnetism, paramagnetism and ferromagnetism. So basically the basic things which we need to solve the problems, we need to know about magnetization. So magnetization is defined as M. M is magnetization. So magnetization is basically the number of magnetic moment per unit volume. Magnetization. Then you know about chi. Chi is called magnetic susceptibility. So in this context we will call it as magnetic susceptibility. And then H is applied strength of the applied magnetic field. So these are the notation used for this chapter, magnetization. So H is the strength of the applied magnetic field. Then B is the magnetic flux or the magnetic induction. Sorry about this. Magnetic flux density or magnetic induction density. And you know the relation between chi and M and H. So susceptibility is defined as M by H. And the magnetic flux B is given by mu naught into H plus M. So let me admit. Yeah. So B equal to mu naught into H plus M. Now you can replace M from this relation, so it will be mu naught into H plus chi H. That is B equal to mu naught into 1 plus chi into H. So this quantity, so mu naught is the permeability of free space, and this is the permeability of the material. So mu is equal to mu naught into 1 plus chi, and this is called the absolute permeability of the medium which we are talking about. Then there is also the relative permeability, which is defined as mu r, and mu r is mu by mu naught. That is mu equal to mu naught into mu r. So these are the basic things you already, I guess, you know. So with this, let's solve few problems, and I'll come to the theory when it is needed for a particular problem. So let's start with this first problem. If any of these problems are already solved, then let me know, then we'll not discuss that particular problem, and we'll go to next problem. So the first problem is this one. A paramagnetic salt contains 10 to the power 28 ions per meter cube, and each ion having magnetic moment equal to magnetic moment of one Bohr magneton. Salt is placed in a magnetic field in a uniform magnetic field, strength H equal to 10 to the power 6 ampere per meter at temperature T equal to 300 Kelvin. Calculate paramagnetic susceptibility. According to the Langevin, Langevin's classical theory of paramagnetism. Bohr magneton mu b is defined. Mu b is equal to 9.27 into 10 to the power minus 24 ampere meter square. So this is the question, and the four options for this question is A equal to 1.15. If you know the answer, you can try calculating it. Meanwhile, I'll write the options. 8.69 into 10 to the power minus 5. Option C is 2.27 into 10 to the power minus 6, and option D is 3.19 into 10 to the power minus 3. So these are the options. So I'll read out the question again. So a paramagnetic salt contains 10 to the power 28 ions per meter cube, and each ion having magnetic moment of 1 Bohr magneton. The salt is placed in a uniform magnetic field, strength H equal to 10 to the power 6 ampere per meter at temperature T equal to 300 Kelvin. Calculate the paramagnetic susceptibility according to the Langevin's classical theory of paramagnetism. And Bohr magneton is also given, mu b equal to 9.27 into 10 to the power minus 24 ampere meter square. So with this information, can you calculate the paramagnetic susceptibility using the Langevin's classical theory, not the quantum theory? So can you calculate this? Let me write down the formula. So using that formula, you can calculate the paramagnetic susceptibility. So the paramagnetic susceptibility, chi paramagnetic, is given by mu naught n mu square by 3 kBt. So this is the formula to calculate the paramagnetic susceptibility using the classical law. Here mu naught is the permeability of free space, n is the number of atoms per unit volume, and n is also given in the question. Mu square is the magnetic moment for per magnetic moment per atom, let's say, and T is temperature. So everything is given. So calculate this. It's just some numerics, and you can get the answer. Let me know if any of these questions have already been solved. If anyone has done this solution, then let me know the answer of this. Shall I solve it, or you can do it? See, and also the value of mu naught is 4 pi into 10 to the power minus 7 in the unit of Henry per meter. So see, in this question everything is actually given. What is n? N is 10 to the power 28 ions per meter cube. Then mu is, so the salt is placed in a uniform magnetic field. Strength is at temperature T equals 300 Kelvin. Calculate paramagnetic susceptibility according to the Langevie's classical theorem of magnetism. Okay, so each ion having magnetic moment of 1 Bohr magneton. So each atom 1 Bohr magneton is 9.27 into 10 to the power minus 24 ampere per meter. Sorry, ampere meter square. Then T is 300 Kelvin, right? Yes. So put these values in formula. Then what will be chi para? So chi paramagnetic is equal to mu naught, which is 4 pi into 10 to the power minus 7 into n, that is 10 to the power 28 into mu square 9.27 into 10 to the power minus 24 square divided by 3 into 1.38 into 10 to the power minus 23 into T is 300 Kelvin. So calculate this. Okay, so someone is there. Now calculate this and let me know the answer. So it is 4 into 3.142 into 9.27 square divided by 3 into 1.38 into 300. So 8.69, it will be 8.69 into 10 to the power so 28 minus 48 plus 23, that is so 10 to the power minus 5. Sorry. So this is the answer and it will match with option B. So if let me know if everyone got this answer. The correct answer is option B. Is there any doubt from this question? So the answer is in ampere. Sorry, the answer is 8.69 into 10 to the power minus 5. If it's clear, then let's solve the next question. The next question is the susceptibility of a paramagnetic material at temperature 300 Kelvin is 2 into 10 to the power minus 5. Then at what temperature its susceptibility will increase to 3 into 10 to the power minus 5. And these are the option. Option A is 100 Kelvin, option B is 200 Kelvin, option C is 300 Kelvin, and option D is 400 Kelvin. So can you calculate this? You just need to say at what temperature the susceptibility will increase to that new value. So this is a paramagnetic material. So for paramagnetic material, that susceptibility chi equal to C by T. So use this formula and calculate the temperature. So C is the constant, then if chi1 by chi2 will be T2 by T1. In our case, chi1 is 2 into 10 to the power minus 5, and chi2 is 3 into 10 to the power minus 5. Then T2 we need to calculate, and T1 is given 300 Kelvin. So according to this, what will be T2? T2 is so 10 to the power minus 5 cancels out. We have 2 by 3 into 300. That means 200 Kelvin. So the right answer is option B again. So the correct answer is option B. Is it clear that chi is inversely proportional to temperature for paramagnetic material? Then chi1 by chi2 is equal to T2 by T1, and we just used the information given in the question. It was an easy question to solve. Okay, now let's calculate the next question. That is question number 3. It is given that assume, if you have any question regarding any of this question, then please ask. Assume that a magnetic dipole whose moment has magnitude magnitude UL is aligned parallel to an external magnetic field whose strength has magnitude B. Now take UL equal to 2 Bohr magneton and B equal to 1 Tesla, and calculate the energy. Calculate the energy required to turn the magnetic field to turn the magnetic dipole so that it is aligned anti-parallel to the field. And 1 Bohr magneton mu B is also given in the question, 9.274 into 10 to the power minus 24 ampere meter square. So again it is a multiple choice question, and the options are 1.13 into 10 to the power minus 3 electron volt Option B is 2.32 into 10 to the power minus 4 electron volt. Option C is 5.53 into 10 to the power minus 5 electron volt, and option D is 6.73 into 10 to the power minus 6 electron volt. So can you solve this question? Please at least try, then I'll solve it if you can't. Hello. So anybody solve this question? What is written in the question? Said assume that a magnetic dipole whose moment has magnitude mu l is aligned parallel to an external magnetic field. So you assume that the magnetic field is along the z direction. So let's say this is the magnetic field along the z direction, and mu l is also aligned parallel to the external magnetic field, and mu l is also along this direction. So you know that the potential energy corresponding to this magnetic moment is given by minus mu l mu dot b or mu l b cos theta. Since it is along that direction, E equal to this. So along the same direction, then theta is 0. That means it is just mu l b. So the question was to calculate the energy required to turn the magnetic dipole so that it is aligned anti-parallel to the field. Now we from this condition we want, so magnetic field is along this direction, but we want this condition that mu l is opposite to the magnetic field. So for this case the energy is mu l b. Let's say this is E1, and for this scenario this energy is mu l into b minus mu l b cos theta. Now cos theta is 180 degree, that is minus 1, that is mu l b. Then the energy required is E is E2 minus E1, which is 2 mu l b. Now in the question, mu L is given. Mu L is 2 Bohr magneton, that is 2 into 9.274 into 10 to the power minus 24 ampere meter square, and magnetic field B is 1 Bohr magnet, 1 Tesla. Is it so? Yeah, 1 Tesla. So put these values in the energy expression, then E will be 2 into 9.274 into 10 to the power minus 24 into 1 Tesla. So this is in Joule. To calculate this one, so let's calculate this. 4 into 9.274 into 10 to the power minus 24. So it will be 3.71 into 10 to the power minus 23 joule. Now the options are given in electron volt unit, so you need to transform this answer to electron volt. So convert this, so the when you divide it by 1.6 into 10 to the power minus 19, then it will be in electron volt. So calculate now this one, 3.71 divided by 1.6, that is 2.32 into 10 to the power minus 4 electron volt. So this is the energy required to make it anti-parallel to the electric field. Is this clear? If this is clear, then let's move to the next question. If you have any doubt, then you can definitely ask. If you don't understand any of the steps, please unmute and ask. Now question 4 is the high temperature magnetic susceptibility of solids having ions with magnetic moment can be described by chi proportional to 1 by t plus theta, with T as absolute temperature and theta is constant. The three behaviors that is paramagnetic, ferromagnetic, and antiferromagnetic described respectively by A is theta is less than 0, theta is greater than 0, and theta is equal to 0. Option B is theta is greater than 0, theta is less than 0, and theta is equal to 0. Option C is theta equal to 0, theta less than 0, theta greater than 0, and option D is theta equal to 0, theta greater than 0, and theta less than 0. So these are the four options. So you don't need to do any algebra or any numerics here. Just this formula you need to know for this chi for paramagnetic, ferromagnetic, and antiferromagnetic. So let me write down the formula. So for paramagnetism, this is the famous formula, chi equal to C by T. So this you already know. So for paramagnetic, theta should be 0, theta equal to 0. So option A and B cannot be true, because for option A and B, theta is either less than 0 or greater than 0 for paramagnetism. So either option C or option D is correct. Now for ferromagnetism, chi is C by T minus Tc. This is the Curie temperature. So here theta is, so if we write at T plus theta, then theta is less than 0. And for antiferromagnetism, chi is C by T plus Tc. So here theta is greater than 0. So which option should be correct? So option C is correct. The correct answer is option C. So it's just these formulas you need to know for paramagnetic, ferromagnetic, and antiferromagnetic material. So this was also an easy question. Let's calculate this one now. So with the given formulas or with the problems we already solved, you can solve this question, and please do it. In a paramagnetic solved, having Fe2 plus ions concentration n equal to 10 to the power 30 ions per meter cube, and the salt is placed in a uniform magnetic flux density, that is B is given as 0.01 Tesla at temperature at temperature T equal to 300 Kelvin. So calculate the magnetization of the sample using the formula. So this formula is also given in the question. You don't need to remember this formula. So the formula for magnetization M is given as N G square mu V square J into J plus 1 into B divided by 3 kVt. The electron configuration for this salt is also you need to know, because otherwise you can't calculate L, S and J values. So configuration of Fe2 plus is ion is 3D2 plus, sorry 3D 3D6, and the constants you already know, so I am not writing the constants of Bohr magnet and kV. So with this the options are 3.1 into 10 to the power 3 ampere per meter. Option B is 5.7 into 10 to the power 3 ampere per meter. Option C is 9.1 into 10 to the power 6 ampere per meter, and option D is 8.2 into 10 to the power 7 ampere per meter. So these are the options. With this, please calculate. The formula of magnetization is also given. Only thing that you need to know is the formula of G, and this is 1 plus 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. So with this formula and the given configuration, please calculate and let me know the answer. এই অমর তো তুমি ওটা দিয়ে দিয়েছিলে তো স্যারকে? Okay, so here S is spin angular momentum, spin angular quantum number. L is orbital angular quantum number, and J is total angular quantum number. So with this, please calculate this one. Has anyone calculated this? It's not that difficult to calculate given the formula and all. So here G first, you need to first calculate what is G. So let me add this. So the electrical configuration for Fe2 plus is 3d6, right? Sorry, let me draw it again. Yes. So 1, 2, 3, 4, 5. Since it is 3d6, we will have first, according to Ohm's multiplicity rule and Pauli's exclusion principle, this will be the electron configuration for 3d6 configuration. And for d orbital, it is -2, -1, 0, 1, 2. These are the L values. So total S is how many electrons are unpaired here? 1, 2, 3, 4. So 4 into, and each of them has spin half. So total spin is S is 2. Similarly, what is L? L is the unpaired electron is this 4. So -1 plus 0 plus 1 plus 2. That means 2. So you can calculate J also. J is L, since it is more than half filled, then it is L plus S, which is 4. For less than half filled, it is mod of L minus S. Less than half filled is not the case, so we will not do L minus S. It is L plus S for more than half filled. So we know S, L and J, all of them. So using this, let's calculate G. What is G then? G is 1 plus J into J plus 1. Let me verify the formula again. Yeah, it is it. J is 4. 4 into 4 plus 1 plus 2 into 2 plus 1 minus L is also 2 into 2 plus 1 divided by 2 into 4 into 4 plus 1, because 2J plus 1, that is 1 plus, so these 2 will cancels out and we will have 4 into 4 plus 1 is 5, 20 divided by 20 into 20 is 40, that is 1 plus 0.5 means 1.5. This is the G value, and other things are already given in the question. So M, let me write down the formula for M. M is N G square mu V square J into J plus 1 into B divided by 3 kVt. Given N, what is N? So number of ions per unit volume is 10 to the power 30 ions per meter cube. Then G is, we have calculated G, which is 1.5. We have mu B square, mu B is 9.27 into 10 to the power minus 24 ampere meter square. Then J is 4, we have already calculated J. B is given, B is 0.01 Tesla, and finally temperature is T equal to 300 Kelvin, and kV you already know, it's a Boltzmann constant. So using this we will calculate M, which is 10 to the power 30 into G square, that is 1.5 square, into mu B square, that is 9.27 into 10 to the power minus 24 10 to the minus 24 square into J plus 1. So J is 4, that is 4 into 4 plus 1, and V is 0.01 Tesla. Now in the denominator we have 3 into 1.38 into 10 to the power minus 23 joule per Kelvin, and temperature is 300 Kelvin, ampere per meter. So yeah, this is the formula. Now calculate this and see which of these options is correct. So let's calculate this. 1.5 square into 9.27 square into 4 into 4 plus 1, that is 520 into 0.01 divided by 3 into 1.38, so 3 into 1.38 into 300, so it is 0.031 into 10 to the power. Now there is 48 minus 30 minus 23, so 10 to the power minus 5 ampere per meter. Is it 10 to the power minus 10 to the power 5, 10 to the power. So according to this, it will be 3.1 into 10 to 10 cube ampere per meter. So this is the answer, and it matches with option A. As we can see, option A is the correct answer. Is it clear? So what we did is we already know the formula which is given in the question. We first calculated G, which is Landage's factor. So G is calculated by this electron configuration. Then we have put all the values which are given in the question already. So that's how we can calculate the magnetization. Now let's move to the next question. So it's a similar kind of question, that's why I'm writing down this question before. So you guys should be able to do this. The most important contribution to the paramagnetism. By the way, if you have any problem, any doubt about these questions we have already solved, you can ask. Paramagnetism of CuSO4 comes from Cu2 plus ions, for which Cu2 plus ion for which the magnetic moment is due to single unpaired spin L is equal to 0, J equal to S equal to half, and G equal to 2. So all of these things are already given, you don't need to calculate. Find out the magnetization M of the CSO4 sample when it is subjected to so sample when it is subjected to a magnetic field P equal to 0.01 Tesla at temperature T equal to 300 Kelvin. The ionic concentration in the sample is N, which is equal to 10 to the power 28 per meter cube, ions per meter cube, and the options to this question are 2.076 ampere per meter, option B is 21.012 ampere per meter, option C is 96.134 ampere per meter, and option D is 109.721 ampere per meter. So it's similar to the last question we have solved, and also in this question L, J and S, G, all the values are given. So using this information, please calculate the answer for this question. The formula is written in the previous question, so using that formula please calculate this, and I'll look to this comment. So what is it? Sir, please give some idea about intrinsic magnetic flux density of europium oxide. So if you write down the full problem, then we can discuss about this. How do I discuss about the intrinsic magnetic flux density of europium oxide? So flux density is B, which is if you apply a magnetic field, then flux density B is, so I have written already the formula. So B is equal to mu 0 into H plus M. So H is the applied magnetic field and M is the magnetization which will be due to this applied magnetic field, and the total effect is the magnetic flux density. So if you know the magnetization and the applied magnetic field, then you can calculate the intrinsic magnetic flux density of any ions or any material. First calculate this problem. Please everyone do this problem, because it is the same problem which I have solved in question number 5. So same to that problem, just need to use that formula and put the values and let me know the answer. And also let me know that if these questions are already solved, because no one is responding actually. Can anyone tell me? Solve this question. I'll be back in 2 minutes.
गंदा यहाँ बैठा हुआ है चला के ये क्लास ऑफ हो गया
दो पिज्जा ऑर्डर किए थे
लेके आता
मैं दिखाया
क्या 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 क्या
रात में नहीं खाएगा ना
हाँ
और रात में इसका पार्टी है ये पार्टी की बात दे रही है बोले तो चलो दे रहे हैं दिवी ना करना एक्स्ट्रा बुक को बोले तो दिवी ना करना कैसा नहीं है भाई
देवो
পরে কোনো
অর্ডারটা করে দিই আইপ্যাডটা অর্ডার করে দিই আইপ্যাডের সাথে খাওয়া দাওয়া সম্পর্ক করে আইপ্যাড থেকে অর্ডার করতে
হ্যালো Has anyone calculated it? So this problem has anyone calculated? Okay, I can't find that. Okay, I found it. So where is the problem to solve this? It's the same question. The formula is m equal to n g square mu v square b into j plus 1 divided by 3 kVt. Given n is 10 to the power 28 per meter cube, g is 2, yes, g is 2, j is half, j is also given, which is half. Then mu b square you already know. B is, what is b? 0.01 Tesla, and kb is given. Temperature T is 300 Kelvin. Yes, so everything is given. Now put this in the formula of the magnetization. M is 10 to the power 28 into g square, that is 2 square, into mu v square, which is 9.27 into 10 to the power minus 24 square, into b, that is 0.01, into j plus 1, that is half into half plus 1, and then you will have in the denominator 3 into 1.38 into 10 to the power minus 23 into T, that is 300 ampere per meter. So this was the same thing we did in the last question. Calculate this and see which of the options is the correct one. And the right answer to this is 2.076 ampere per meter. This was easy, right? So there is this question. First I will solve it and then we'll move to the doubt about this, which you have posted in the comment. So let me write down this question. This was question number 6. Then question number 7. Calculate the approximate value of the magnetic flux for the orientational potential the energy required to align the magnetic field magnetic dipole along the direction of the applied magnetic field. Of the magnetic field be comparable thermal energy at room temperature
আজকে না
300 Kelvin. Assume the dipole moment of a magnetic dipole to mu v. So the question is calculate the approximate value of the magnetic flux density for the orientational potential energy the energy required to align the magnetic dipole along the direction of the applied magnetic field be comparable to the thermal energy at room temperature, and where T is given as 300 Kelvin, then assume the magnetic dipole moment of a magnetic dipole is mu m equal to 2 mu v. Mu v is the Bohr magneton, and the one Bohr magneton is equal to 9.27 into 10 to the power minus 24 ampere meter square. And Boltzmann constant is you already know. So using this information, please calculate the question, and these are the given option 101.3 Tesla. Option B is 223.3 Tesla. Option C is 413.5 Tesla, and option D is 693.7 Tesla. So please calculate this one. What should I look for? What is the due date to this? So what is the answer to this question, if anyone has calculated? And about the question of assignment 11, so I cannot discuss about a question assignment 11 because the due date is today, so it's unfair to discuss anything about question number 11 as it was instructed to us to not discuss the assignment which the due date is not over for which assignments. So if you submit the assignment, and then we can discuss about it in the upcoming session, let's say in Saturday. Okay. So I'll suggest read some textbook, let's say KTEL or something. You'll get idea about this question. So from the question, you can see that you need to calculate the B, that is the magnetic field, because it is the options are given in units of Tesla, right? So using G and G value and J, you need to calculate. And since G and J these are given, so you need to uh, adopt the quantum mechanical approach and calculate the intrinsic density, intrinsic magnetic flux density. So refer to any textbook, you'll definitely can solve the question. Do you know about Kittel or Puri Babbar? So I'll write. Okay, so let me. So before that, please solve this question, please. me calculate this then. So in the question it was said that the magnetic flux density for the original potential energy is comparable to the thermal energy. Now to align this, the what is the energy? Mu b into b, and that is comparable to thermal energy, that is kBt. You need to calculate the b, and b is kBt divided by mu b. Now kBt is 1.38 into 10 to the power minus 23 into 300 and divided by mu b. Mu b is it is mu dot b. So mu is mu b into the magnetic flux. Assume the magnetic dipole moment of a magnetic dipole is 2 mu b. So 2 into, so it is 2 mu b, that is 2 into 9.27 into 10 to the power minus 24. This Tesla. Then calculate this. So what is the value of this? 1.3 into. So what is the value of this? Please calculate. Yes, option B is correct. So that is 223.3 Tesla. Option B. Yeah. So there is this question. I think everyone should solve this. This kind of question appears in any competitive exams also. So this is question number 8, not 10. Use the given relation. That A is equal to S1 plus S2 and find out the value of exchange interaction. Find out the value of exchange interaction, which is minus 2 JE S1 dot S2, given that S1 S square equal to 0 and S1 square equal to S2 square equal to 1 by 4. Then the options are A equal to JE, B is equal to JE by 2. Option C is 2 JE and option D is 3 by 2 JE. So calculate this. So someone has calculated already and saying option B. Yes, so for this question option B is correct, because first you need to just need to calculate what is S1 dot S2. How do you calculate S1 dot S2? S is given S1 plus S2. Then what is s square? S square is s1 square plus s2 square plus 2s1 dot s2, which implies that 2s1 dot s2 equal to s square minus s1 square plus s2 square. Now s square is 0 and s1 square is and s2 square both are 1 by 4, that is minus half. So you put this value in exchange energy. So the exchange interaction is minus 2 JE JE minus 2 JE, and 2 S1 S2 is equal to minus half, that is JE by 2, and this is actually option B. Then there is another short question. Using the electron configuration, you can calculate these also. So calculate effective number. Question number 8, 9, 7. Calculate effective number of Bohr magneton P effective equal to G into root over of J of J plus 1 of the ions Gd2 plus having electronic configuration F7 5s2 5p6. So using this electronic configuration, calculate the effective number of Bohr magnetons. And this 9.74, so 7.94. 7.94, option C is 2.68, and option D is 3.62. Calculate this. G equal to 2, J equal to 0.5, then option 7.94. Yes, so the electric configuration is basically 4F7. So 7 electron will be in the 7 orbitals this way, so all of them is unpaired. Since it is so this is minus 3, minus 2, minus 1, 0, 1, 2, 3, these are the L values, and AC is 7 into half, that is 7 by 2. Since since the orbital is exactly half filled, then L is equal to 0, and J will be L plus S, that is sorry, L is 0 and J is L plus S, which means it is also 7 by 2. So J is not 0.5, J is 7 by 2. And G, so G is 1 plus J into J plus 1 minus plus S into L plus 1 minus L into L plus 1 divided by 2 into J plus 1. Now L is 0 and S is equal to J, so it will be 1 plus 2J J plus 1 plus J into J plus 1 divided by 2J into J plus 1, that is 1 plus 1, because in the numerator also it is 2 into J plus 1, so G is 2. So yeah, G is 2 and J is 7 by 2. So using that you can calculate P effective. So P effective is equal to G into square root of J into J plus 1. So J is 2 into 7 by 2 into 7 by 2 plus 1, which will be 2 into root over of 63 divided by 2. 2 cancels out. This is root over of 63, and root over of 63 is 7.94. Is it clear? So the answer will be 7.94. That is option. The correct option is option B. So we can solve another question, I guess, because we still have some time. And there is this question. This is also a short question. So calculate, and it's similar to the previous one. Effective number of Bohr magneton root over of S into S plus 1 for the ion Ni2 plus, which belong iron groups. That is 3D groups. Three D group ions. Having electron configuration 3D8. The options are: option A is 1.73, option B is 3.87, option C is 2.83, and option D is 4.90. So first calculate S and put that in the formula. Please do it early, we don't have much time for. So this will be the last question for today. So you are saying option C is correct. Yes. So in this question, Ni2 plus is 3D8. I'm sorry. So this is -2, -1, 0, 1, 2. This is up, 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 down, down, down. So there are two unpaired electrons, so S will be 2 into half, that is 1. Since S is all we need, then P effective is equal to 2 into root over of S into S plus 1, and that is root over of 2 into 1 into 1 plus 1, that is 2 into root 2. And what is the value of that? I guess it is 2.83. So the correct option is option C. Yeah, so S is 1 and you just needed to calculate the S. And about your question, MDIO, you are asking for to find the intrinsic magnetic flux density of europium oxide at 0 Kelvin, right? So
Yes,
if,
sir.
yeah, so if, do you have the book of Puri Babbar?
Sir, I have no book, any book.
Okay, so there is this formula in the book. You can use that formula to calculate that. So uh, B is this effective magnetic field flux density. B is equal to lambda into m,
Yes, yes, sir. Yes,
and then lambda into m, since it is at 0 Kelvin temperature we need to calculate. So it is the spontaneous magnetization, m is 0. So the formula will be replaced as lambda n g j mu b. So using that, and there is some other equation, you can finally get this formula, that
please, sir, repeat lambda, revised formula. Please repeat.
so 3k Tc divided by g mu b into j into j plus 1. So in this formula, this, you know, Tc, you know k, you know j
Yes,
and g, all of these are given. So using those values you can calculate what is Be.
okay, sir.
So that was the question, right? To find the intrinsic flux density. So B is the intrinsic flux density. So Be is equal to lambda into m. So at 0 Kelvin it is lambda into m is 0. That is the saturation magnetization, and this formula will be lambda into n into j into j mu b. Since lambda is not given, but you can replace this by the other equation. So let me write down the equation. So there is this equation for Tc, that Tc equal to lambda into n v square mu v square into j plus 1 divided by 3k. So from this formula you can replace lambda in this b equation of Be, and then you finally will get this formula. So write down this formula. This is the main formula for your question. Be equal to 3k Tc divided by j mu b j into j plus 1. So if you
Sir,
yeah,
sir, in this specific case, how can we calculate capital N?
capital,
N.
so
Now, number of.
capital N is also not needed in the final case. This formula you don't have capital N. Do you have capital N here?
Okay, okay, sir.
So basically n lambda is replaced by this formula, and so here is also n lambda. So this n lambda is replaced by, so this is the final form, and in this form all the values are given in the question. You don't need a capital N or lambda.
Okay, sir. Thank you, sir.
Is there any more question?
No, sir. Okay.
Okay, then we'll end here. We'll meet. So for the last class on Saturday we'll meet. So thank you everyone. Bye.